Hello everyone and welcome to our module on statistics. Let's start by talking about statistical distribution, and in order to understand this, let's imagine that we took a bunch of healthy subjects and we randomly measured their blood glucose at a time when they were fasting. If we did that, we might get a whole bunch of numbers like what I've shown on the slide here. And as you can see, some numbers occur only once in one individual, whereas other numbers occur in multiple individuals. If we then made a graph of blood glucose level along the x-axis and the number of subjects that had each value for blood glucose level, we would get a distribution that looks like this. And this is called a normal or Gaussian distribution. And normal distributions like this are very common for natural phenomena. You can see it for blood glucose level. You can also see it for mean blood pressure. You can see it for height. Many things in nature tend to cluster around a central value, with that value occurring very commonly in nature, and then values below or above that central value occurring less frequently. So now let's talk about central tendency, which refers to the center of a normal distribution, like what we saw in the last slide. And in statistics, we characterize the central tendency of data that are normally distributed in three major ways. The first is by the mean value, which is the average of all the numbers. The second is the median value, which is the middle number of a data set when they're all lined up in order. We'll talk more about this in a minute. And the third way is by the mode, which is the most commonly found number. So mean and mode are fairly easy to understand. Let's imagine we took 6 blood pressure readings and we got these 6 values I've shown on the screen here. Well, the mean is simply the total of those values divided by 6, which is the number of readings, and that would be 96.7. The mode is the most frequent number, and as you can see, that's 80 here, so the mode would be 80. In order to determine the median for a set of numbers, you have to line the numbers up in order. Once you do that, the median is the middle number, but the number you pick depends on whether the data set has an odd or even number of elements. So for example, let's say we had 3 measurements, 80, 90, and 110. We've lined them up in order, so the middle number is the median, and that's 90. And this is what you do when you have an odd number of data elements in a set. If you have an even number, though, then you still line them up in order, like I've done here, 80, 90, 110, 120. But in this case, there is no middle number because you have an even number of data elements. So instead, what you do to determine the median when the number of data elements is even is you take the halfway point between the middle pair. So in this case, the middle pair is 90 and 110, so the median is halfway between those two numbers, which is 100. And a key point here, which hopefully you appreciate, is that in order to determine the median, you have to put the data set in order. This is something that you don't need to do in order to determine the mean or the mode. So when you have a normal distribution of data elements like what's shown on the screen here, and you have an even number below and above the center of the distribution, then the mean, median, and mode are all going to be the same number, this number right here in the middle of the data set. The mode is easy to identify visually from a data graph like this because the mode is always the highest point. The highest point is the blood glucose value that the most subjects have, and so that's necessarily going to be the mode. And then if the distribution is even with equal numbers above and below the center of the distribution, then the mean and median are going to be equal to the mode. Sometimes, however, data are not evenly distributed, and this is called skewed data or skewness of data. And in this situation, the mean, median, and mode are not going to be the same. So if you look at this data chart on the left side of the screen here at the bottom, you can see that it has this tail going down towards the low numbers of the x-axis. So when the data looks like that, we say it is negatively skewed. On the right, you can see that this data set has a tail that's going towards the higher numbers on the x-axis, and we call that positively skewed data. So the skewness of the data is named positive or negative based on the location of the tail of the data. As I said before, the mode is always easy to find. That's the highest point, and you can easily identify it in the negative and positive skewed data shown on the screen. But then the mean is always going to be towards the tail, with the median in between the mean and mode. Same thing for positive skewed data. The mean is always towards the tail, with the median in the middle between the mean and the mode. So on this slide, I've summarized the key points about central tendency. They sometimes ask you about this on your board exams. If the distribution is equal, then the mean, mode, and median are all equal to one another. The mode is easy to find. It's always the peak of the data set when shown in a graph. And when you have skewed data, the mean is always furthest away from the mode towards the tail, and the median is in between the mean and the mode, just like I showed you on the last slide. And then another thing to know, because they like to ask you about this on your board exams, is that the mode is the least likely descriptor of central tendency that will be affected by an outlier. An outlier is a data value that's either very, very high or very, very low, far away from the other data elements. And so when you add one outlier, that's going to change the mean and the median, but it only affects the mode if it changes the most common number, because remember, the mode is the most common data set number. And one outlier is very unlikely to change the most common number in a data set, so usually the mode is resistant to change when outliers are present in a data set. On the other hand, outliers can affect the mean and the median. Now let's move on from central tendency and talk about dispersion of data sets. Shown on the screen are graphs of two data sets of blood glucose values. Both graphs show normally distributed data, and in both graphs the mean, median, and mode value is 100 milligrams per deciliter. But hopefully you can appreciate that the two data sets are very different. This one is very tightly clustered around the middle value, the mean, median, and mode value, and this one is more dispersed and spread out. And so what's different between these two data sets is the dispersion of the data, so let's talk about that now. There are a number of different measures that can be used to describe the dispersion of a data set. The most important one is the standard deviation, but we'll also talk about two others, the variance and the z-score. Standard deviation is the most important dispersion measurement, and we denote the standard deviation for a data set by the Greek symbol sigma. And standard deviation is equal to this equation shown here. To calculate the standard deviation, you need to determine the difference between all the data points and the mean for all the data points. That's x minus x mean. You then sum those differences and square it, and you divide that number by the number of samples minus 1, and then you take the square root of this whole term here. So to make this more clear, I've created two data sets, group 1 and group 2, and they both have the same mean value, which is 10, but they have different dispersions, which means they're going to have different standard deviations. So this is the equation for standard deviation, and so in order to use this equation to calculate the standard deviation for group 1 and group 2, the first thing we have to do is determine the differences between each data point and the mean value, which is 10. Once we have those differences, we square them, and then we total that up, and that gives us the sum of all the x minus x means here squared. That works out to 11 for group 1 and 96 for group 2. We then divide that value by n minus 1, which is 7 for both groups, and we take the square root, and we get a standard deviation of 1.24 for group 1 and 3.7 for group 2. And so group 1 has a very low standard deviation. That means the data points are tightly distributed around the median value as shown in this graph. Group 2 has a much larger standard deviation, so those data points are more dispersed and more widely spread out, just like shown in this graph here. And so the standard deviation is a number, but it gives you an idea of what the data would look like if they were on a graph in terms of how much dispersion is present. Once you know what the standard deviation is for a data set, the percentage within plus or minus a standard deviation is always going to be the same. So if you have normally distributed data like shown in this graph here, within plus or minus 1 standard deviation you will always find 68% of the data points. Within plus or minus 2 standard deviations you'll find 95% of the data points, and within plus or minus 3 you will find 99% of the data points. And it doesn't matter how dispersed the data is, you will always find that same percentage of data points within plus or minus a standard deviation. So if you look at this narrowly dispersed data set on the left, we still find 68% of the data points within plus or minus 1 standard deviation, and 95% within plus or minus 2, and 99% within plus or minus 3. The same is true of the data set on the right. We still find 68% of the data points within plus or minus 1 standard deviation. But remember, the standard deviation is larger for more dispersed data sets like this, so you have to look at a wider collection of data points in order to capture that 68% compared to the narrowly dispersed data over here on the left. So here's a sample question to give you an idea of how you might be asked to apply the concept of standard deviation. Let's imagine we measure fasting glucose in 200 medical students, and the mean value is 100 with a standard deviation of 5. The values are normally distributed, and the question asks how many students have a glucose greater than 110. Well, we have all the information we need to answer this question. So 110 is 2 standard deviations away from the mean, because the mean is 100 and the standard deviation is 5. So as we discussed before, 95% of samples fall within plus or minus 2 standard deviations. That means 5% of samples fall outside this range, 2.5% below this range, and 2.5% above this range. And this number right here represents 110. That's 2 standard deviations above the mean. So 2.5% of students are going to be above 110. That's half of 5%. And 2.5 of 200 students is 5 students, and therefore the answer is 5 students. Another measure of dispersion in a data set is variance. This is related to standard deviation. The variance represents the average degree to which each data point differs from the mean. If you look on the screen here, this is the equation for standard deviation once again. The equation for variance is shown here. Variance is sometimes called sigma squared, and it's equal to this term here, which as you can see is very similar to the term used to calculate standard deviation. And then finally, let's talk about z-score, which is related to dispersion. So standard deviation and variance describe the dispersion of an entire data set. The z-score describes a single data point, and it's a representation of how far that data point is from the mean in terms of standard deviations. So if a single data point is equal to the mean, then that data point has a z-score of 0. A z-score of +1 means the data point is 1 standard deviation above the mean, and a z-score of -1 is 1 standard deviation below the mean. And I've shown these on this graph on the screen here. So a z-score of 0 is a data point equal to the mean, and then we have z-scores of -1, -2, and -3 going in this direction, and +1, +2, and +3 going in this direction. So for example, suppose a test had a grade average or mean equal to 79, and the standard deviation was 5. Well, if your score was 89, then you are 2 standard deviations above the mean, so your z-score is going to be +2, which you can calculate from this equation here. I'm going to finish this video by talking about 2 important statistical terms that are used to describe how a data set relates to the true population mean. So suppose we take 100 samples to estimate the population mean glucose level. Now we've only taken 100 samples, but the total population is 1 million individuals. So what we like to describe in statistics is how close we think our sample mean is to the true population mean. In epidemiology studies and clinical trials, we're always studying a sample of patients. We never study the entire world population of patients. And so we use statistics to report how close we think our sample mean is to what we would find if we were able to sample the entire population. And the 2 important metrics we use to describe this relationship between our samples and the true population mean are the standard error of the mean and the confidence intervals. The standard error of the mean is a representation of how far our data set mean is from the true population mean. And you can calculate the standard error of the mean by using this equation shown on the slide here. It's equal to the standard deviation divided by the square root of n, which is the number of samples in our data set. So remember the example I gave on the last slide. Suppose we study 100 individuals, and we want to describe how likely we think those 100 individuals represent the total population of 1 million individuals. We can describe this with the standard error of the mean. If our sample of 100 individuals has a very low standard deviation, then we're going to have a very low standard error of the mean, and that means we're closer to the true mean of the population. Along those same lines, if we have a very large number of samples, then that will also give us a low standard error of the mean, and that also means we're closer to the true mean. So when your data set has a small standard deviation or a large number of samples, both of those things shrink the standard error of the mean and indicate that you are likely closer to the true mean that you would find in the total population. Related to the standard error of the mean are the confidence intervals. The confidence intervals are a range of numbers in which 95% of repeated measurements would be expected to fall. So what this is saying is if we repeated our experiment and collected 100 samples, 95% of the time we should get a mean that falls within the confidence interval range of numbers. Another way to think about this is the confidence intervals represent a range in which there's a 95% chance that the true population mean will fall. And the confidence intervals, as I said, are related to the standard error of the mean. They can be calculated by this equation here. The 95% confidence interval equals the mean for your data set of n number of samples plus or minus 1.96 times the standard error of the mean. This is easier to understand if we go through an example. So let's imagine we have a data set with 16 samples. The mean value for the samples is 10 and the standard deviation is 4. Well, as we talked about earlier, the standard error of the mean is going to be equal to the standard deviation divided by the square root of the number of samples, which is 16. That works out to 4 over 4, or 1, for the standard error of the mean. The confidence intervals, therefore, are the mean, which is 10, plus or minus 1.96 times the standard error of the mean, which is 1. And this works out to essentially 10 plus or minus 2. So what we're saying here is that we think if we repeated this experiment and took another 16 samples, 95% of the time the mean for that repeated experiment would fall between 8 and 12, because 10 plus or minus 2 is a range from 8 to 12. Or still another way to say this is that we think the true population mean has a 95% chance of falling between 8 and 12. And we sometimes refer to the number 12 as the upper confidence limit and the number 8 as the lower confidence limit. Now let me make one important point around confidence intervals, especially when it comes to answering board questions. Don't confuse standard deviation with confidence intervals. Standard deviation is a dispersion metric that applies to a data set. So for example, suppose we have 10 samples. These samples have a mean value and a standard deviation. And as we talked about earlier, you can find 95% of the samples between plus or minus 2 standard deviations from the mean. This is a descriptive characteristic of the samples in the data set. In contrast, confidence intervals does not describe the samples in the data set. It's something different. It's an inferred value of where the true mean lies for the population relative to the samples in the data set. So make sure you understand this distinction. So in a board question, when they mention the number 95%, this can be confusing, and you want to read carefully to see what the question is asking for. Are they talking about a set of data, or are they talking about the true population mean? If they're looking for the range in which 95% of the measurements in a data set fall, then what they want is the mean plus or minus 2 standard deviations. On the other hand, if the question is asking for the range in which the true population mean most likely falls relative to the mean in the data set, then they're looking for the confidence interval of the mean, and that's the mean plus or minus 1.96 times the standard error of the mean, just like we talked about earlier. And that concludes our module on statistics.